The mean of a data set is the most widely reported descriptive statistic in just about every field. However, the standard deviation, which is usually reported alongside the mean, is often overlooked but also gives us a lot of useful information and context. In this video, we're going to talk about why means and standard deviations are a dynamic duo just like peanut butter and jelly, and how understanding standard deviations can help broaden your perspective and sharpen your critical thinking. When you have a data set, it can be hard, if not impossible, to draw conclusions just by looking at the raw numbers. The limits of the human brain prevent us from effectively extrapolating broad, meaningful patterns from what could be hundreds or even thousands of individual data points. If you want to know what the overall trend in your data is, the best place to start is by looking at its central tendency. The central tendency of a data set is the descriptive statistic that best summarizes the overall trend in the data. When data are normally distributed, the most common representation of central tendency is the mean. When data aren't normally distributed, the central tendency is often represented by the median of the data set. We'll be discussing the difference between mean and median and when each one is used in a future video. For now, we're just going to focus on the mean. Let's look at a concrete example using a simulated data set. Say I decide that I want to track how long it takes me to drive to work every day because my commute is very unpredictable and I want to get better at planning around it. So each morning after I park at work, I go into my notes app and write down how many minutes it took me to drive from my home to my office. After a year, I have 300 data points, or 300 days on which I tracked my commute to work. First, I should check and see how my data are distributed. If they're normally distributed, then we can use the mean as the indicator of central tendency. When I plot a histogram of these data, I can see that they roughly make a bell-shaped curve, so we'll go ahead and use the mean as our measure of central tendency. To calculate the mean of this data set, or my average commute length, I sum over all 300 commute times, then divide that sum by the number of unique data points I have, which is 300. Doing this gives me a mean of 50. So my average commute length is 50 minutes, with a minimum of 17 minutes and a maximum of 88 minutes. I now know the central tendency of my commute data, but with such a wide range of possibilities, if one day my commute takes me 20 minutes and on another day it takes me 80 minutes, that doesn't do much to help me plan. Side note, if this range of commute time seems far-fetched, you might never have commuted in the Boston area before. While knowing the minimum, maximum, and average of my commute time could be helpful, there's a lot more we can learn from the data we collected, and this is where the standard deviation comes in. In the simulated dataset, the standard deviation came out to be 10. From this one additional piece of information, I now can figure out a great deal more about my commutes. Let's shift to a graph where we can visualize what we're talking about. We know from earlier that our data follow a bell curve shape roughly, and we know that our mean commute time is 50 minutes. As a side note, in statistics, the mean is represented by the Greek letter mu. When you open a stats book and see all the Greek letters, it can be overwhelming. However, it's useful to start to learn them one at a time because it ends up being much more confusing down the road using the words mean or average to talk about data when those words also have widely used regular conversation meanings. You know what I mean? In this case, mu equals 50, which marks the center of our normal distribution. Now I want you to think back to elementary school. You may have learned math using a number line, or maybe there was just a number line hanging up in your classroom. You can think of the mean like 0 on the number line. This might seem confusing at first, but think of it like using a kitchen scale. Pretend you're about to weigh flour and you put the bowl on the scale first. The bowl itself has weight, so you press tare to reset the scale to 0. You're not saying the bowl weighs nothing, you're just telling the scale to start counting from here. You're recalibrating it. That's exactly what we do with the mean when the data are normally distributed. We recalibrate our scale so that the average is set to 0. It's not that the data have a mean of 0 now. We know our mean is 50 minutes. We've just adjusted it so that we can easily compare the rest of our data to it. So it's just a number line with our bell curve superimposed on top of it. It's no different. Each of these reference lines marks one standard deviation away from the mean. Since we know we have a mean of 50 and we know we have a standard deviation of 10, we can figure out what value should be at each reference line. One standard deviation above the mean is 60. We know this because it's our mean of 50 plus one standard deviation of 10, which is 60. So we can put 60 here. Two standard deviations above the mean is 70. And we know that because, again, we have our mean of 50 plus two standard deviations of 10. So 50 plus 20 gives us 70. Lastly, three standard deviations above the mean is 80. Our mean of 50 plus three standard deviations of 10. 50 plus 30 gives us 80. Now we'll label the other side. One standard deviation below the mean is 40, and that's our mean of 50 minus one standard deviation of 10. Two standard deviations below the mean is 30, our mean of 50 minus two standard deviations of 10. 50 minus 20 gives us 30. Lastly, three standard deviations below the mean is 20, our mean of 50 minus three standard deviations of 10. 50 minus 30 gives us 20. Now, for the final step, and to get the most from our data, we have to pull up a statistical reference guide and compare our data to it. This chart and the percentages in it are a universal frame of reference we can use to contextualize our data when they're normally distributed. Each section underneath the curve in this chart shows where different values fall in relation to your mean. For example, we know that 68% of the values in our data set fall within one standard deviation of our mean. And that's that middle 34% plus 34%. So 68% of my commutes are between 40 and 60 minutes. That's what makes this reference chart useful. It gives us a universal frame of reference to compare our data against. So now that you have some familiarity with it, let's take it a little further and apply it to our data. Very few of my commutes are extremely short or extremely long. Those commutes are on the tail ends of my distribution and make up a really tiny percentage of my total commutes. However, that still means there's a wide range of variability in my possible commute time, all the way from 17 to 88 minutes. So, like we said before, if I wanted to make a guess about how long my commute might take on an average day, I could guess 50 minutes. However, by taking into account the standard deviation and using this reference guide, it looks like I should probably plan on at least a 60-minute commute, because I know that 84% of my commutes are 60 minutes or less. I reach that number by summing over the percentages that encompass all the values leading up to my specific value of interest, which was 60 minutes. If I wanted to be even more cautious in my planning, I might allow for up to 70 minutes for my commute, because I know that 98% of my commutes fall at or below that time. I got to 98% because, recall, we just summed up the percentages below the chart space up to one standard deviation above the mean, which was 60 minutes. Now we've moved up to 70 minutes, which is two standard deviations above the mean, which then encompasses an additional 14% of our sample. So we know that 98% of our commutes are 70 minutes or less. Of course, we can't predict road work or car accidents, But using what we know about statistics, we can make more informed guesses about how long things take, like an unpredictable commute. It's important to note that we're talking about descriptive statistics here, not inferential or predictive statistics. We're using the standard deviation to summarize the spread of the particular data I collected. I'm not trying to make an inference about a larger population, or even another person. The data I collected about my commute probably wouldn't translate to your commute. Not that many other people don't have a 50-minute commute, but rather the likelihood of someone having a 50-minute commute and also the exact same spread of data that I have is unlikely. If this were a research study and we wanted to make claims about a population based on our sample, we would talk about the standard error of the mean, not the standard deviation. We'll cover the difference between the standard error and the standard deviation in another video. For now, the take-home message is, the mean gives us the central tendency of a normally distributed dataset, and the standard deviation tells us how the data are spread around the mean. On their own, they're okay, but together, they are much better.